Hello, everybody. Welcome to today's current seminar. Today we have two talks, two speakers. Our first speaker is Alexander Heinlein. He will be giving a talk on domain decomposition for physics-informed neural network. Alexander is an assistant professor in the numerical analysis group of Delft Institute of Applied Mathematics, Faculty of Electrical Engineering, Mathematics, and Computer Science. At Delft University of Technology, TU Delft, specializing in numerical methods for partial differential equations and scientific computing. His expertise extends to high-performance computing and the intersection of scientific computing with machine learning, with a PhD from the University of Cologne and a postdoc tenure there. He has also served as a full professor for numerical mathematics for high-performance computing at the University of Stuttgart before his current role at TU Delft. With that introduction, the floor is yours and you can start your presentation.
Yes, thanks a lot for the kind introduction and also for inviting me. It's a pleasure for me to have the chance to speak here. I think in front of many people who know about these, about pins much more than I do. I should really also say that I'm coming more from the domain decomposition part of my title. So I might also not be the person to answer all the detailed question on pins. Luckily, also some of my co-authors are here in case there are, I cannot answer all of the questions. And yeah, I also have some basic introductory slides, which I try to go over a bit more quickly because I expect this will be kind of known to everyone. So I'm more coming here from the left side of let's say scientific machine learning, which from my perspective, I understand as a combination of numerical methods and machine learning, or scientific computing and machine learning. And so I was used, or by training, I'm used to working with physical models, which are really robust and generalizable. But it's let's say that we need those models, and in case we have data, it might be tricky to kind of incorporate that. On the other hand, or machine learning models, which are mostly based on data, and then we, of course, can inherit problems that come from data. So we try to combine those techniques. I think this is well known here. And I will be talking about domain decomposition for physics-informed models, or physics-informed machine learning models. And this is basically partitioned into three different topics, which is also, research with let's say, three different group of people, which you can see here. And yeah, first, this is really a basic introduction just to have everyone on the same page. So I will be talking about an approach which, to my understanding, mainly traces back to somehow this paper from more than 25 years ago now, where a collocation method has been, let's say, used to solve this, let's say, residual-based formulation of a partial differential equation. And here the idea is to plug in a parameterized function, and a very rich class of parameterized functions that you could use are neural network functions. And then by training the neural network via this collocation approach, you can try to solve the partial differential equation. And something that they did in this earlier work is directly making making a nice approach where they really construct the trial function such that they explicitly solve the differential equation. And the reason why this all works nicely is because any state-of-the-art neural network library will give you the opportunity not just to propagate forward through your neural network, but also backward. And by that also being able to compute derivatives, which enables you to evaluate the residual of the differential equation. Yeah, and then you see that, this is really basic here, but the higher, let's say on the left, you see an example. It's a simple PDE or 1D. It's even just an ODE here. You see if the residual is high, which is here in red, then maybe we are far away from the exact solution, which is the dotted line. But if the residual is getting smaller, we kind of fit the actual solution more and more closely. So I think this is, I think in this audience, well known. And I will be talking about the method, which is now well known as pins, which is has been introduced under this name in a paper by I think some of the participants or some of the people in the audience, including George, which is basically, my understanding, an extension of this this earlier method, in the sense that it is kind of let's say brought into this regime where we want to combine physics and data. So we do not only deal with this residual-based loss of the PDE, but we also add a second loss term, which allows us to incorporate data. And this can be data from sensor measurements, or so. It could also be boundary and initial data. So we kind of can cover the whole range of having small data and a lot of physics, up to having a lot of data and little physics. Okay, and then there are some advantages and maybe drawbacks. And well, a lot of people are working on this, so this might, of course, be let's say quickly evolving, and I'm not really aware of all the work that has been done on this because there's just too much going on. Some of the advantages that I would like to highlight is that due to the fact that this is typically done with the Monte Carlo type sampling, it is nicely suited for high-dimensional problems, and it kind of automatically gives you the chance to also solve an inverse problem or parameter-dependent problem. But some of the difficulties include maybe the training and also dealing with, let's say, scaling these kind of networks, and especially also in the context of multi-scale problems. Whereas I don't want to say that there is no way of doing these things, but if you take the plain vanilla pin, like these things can be quite challenging. Just let's say some further remarks on this, also showing a bit this context. So there has been a paper by Sid Mishra and co-author who in 2022 looked a bit into error analysis for this. And without going through all the details here, which is not what I want to do, what I basically just want to point out is that if you, for example, look at this error bound here, there is two additive terms. One part here on the left, where I highlighted this training error, and then there is another part on the right, which depends on, for example, quadrature rule, number of training points, and so on. And something we notice is that the right part can be kind of controlled by adding more points, and maybe taking a better quadrature rule. But I mean, it's the optimization problem is usually non-convex, and the left part is not generally easy part to control. So even if you have a very rich neural network with high capacity, you might be kind of limited due to this training error. So if you can train your pin well, you will get a good solution, or you are able to get a good solution. Something that has also been noticed, so I'm just setting the stage a bit for what I will be talking on, is that there is something which is often called spectral bias for neural networks. So this here is the context of a pure function approximation, so it's just fitting the data. So it's not a pin example that I'm showing here, it's from this paper from 2019. And something that you notice is if you look at the iteration, you first basically get the low frequencies of your solutions, and then after many iterations, you get the high frequency part. So if you want to train, for example, for a multi-scale problem where you have both low frequencies and high frequencies, this is a challenging application for neural networks, and also then for pins if you don't add any special tricks to it. And there has also been work investigating this. And to illustrate this for a very, very simple example for pins, I'm taking this example that has been shown in a paper by Ben, who's also co-author of one of the works I will be showing, where basically here they look into a simple ODE model, and if you just have a low frequency solution that you're trying to approximate, you can take a quite small pin with a low number of free parameters, and you can fit the solution quite well. This corresponds here to this red loss curve. And then if you if you increase the frequency of the solution, the same network will not be able to approximate that well, unless you maybe work with some, let's say, some activation that accounts for this wave nature of the solution. But if you just take a standard pin, and this is not really a problem of neural networks, of course, because even with the classical discretization, you need a certain number of interpolation points or so to approximate a high frequency solution. But then something that unfortunately happens here, again, I'm not claiming there's no way of making it work, but if you just increase the number of parameters here to a quite large network, you still don't really fit it very well, at least at the, let's say, outer boundary parts here of our domain. And this also you can see in the loss. So it's, I mean, it is better than what we had on the top right, but it is not really, maybe not satisfactory yet. So there is some kind of an issue here. And what I want to be talking about, and as I said, it's more, I want to, let's say, a bit give some ideas on how you could do this instead of talking always just about state-of-the-art techniques. The actual thing that I want to show is that maybe if you decompose this very high-frequency solution into local parts, so if you decompose your domain, you can make them look more like this easy one. So you might be able to approximate this well, even with a smaller network, right? Without having to go to a very, very large network that is difficult to train. So I don't know if everyone is very familiar with domain decomposition in the audience, and I will not give a complete introduction. I just want to highlight very briefly that this is a very old approach, actually, in some sense. So it has been introduced as actually a technical tool for proof to show that harmonic functions on non-standard domains exist. And this original Schwartz method basically converges towards the solution on this domain by solving on easy or simple domains where you know solution exists. And the basic property here that gives you the convergence is this overlapping region here between those two geometric shapes. And these, I will show a bit later how we do this with pins. And this is used a lot in science, let's say scientific computing. These type of methods can give you, if you use it actually in the context now as a solver to really compute the solution, they help with robustness and scalability. And they're also well suited for parallel computing, of course, because you can split the problem into smaller problems. And it's not the work that I'll be showing is not the first work on combining these ideas. So there has already been, to me, a surprising large number of papers on the combination of domain decomposition and neural network-based discretization methods. And I'm listing some of those here. There are some which are more based on, for example, C-pins and X-pins in their original way. They have been introduced more for non-overlapping domain decomposition. And then there are some other approaches that are more, have been introduced for more overlapping domain decompositions. And there are, on the bottom, because this is not a full overview, you can look into those maybe survey review papers. There's a, let's say, larger or more complete overview over the literature on this. And so the first two parts of this talk will be about two different extremes of how you could try to incorporate an overlapping domain decomposition into pins. And then the last part will be going a bit more towards not a spatial decomposition, but a temporal decomposition in this talk. And the two extreme examples, the top one is actually you do what has been already done more or less in this very old approach with some slight modification. But the idea is that we introduce a Schwartz iteration, which is nothing else than a fixed point iteration. And within each of those steps of the fixed point iteration, we solve a local problem on each overlapping subdomain. And then between these iterations, we exchanged information somewhere in the overlap. And then you see that eventually maybe you converge to a solution everywhere. So it's a bit So you see a bit, they are supposed to be overlapping these, and then at some point they converge to a complete solution. And the other extreme is that we don't have, we just incorporate this in the network architecture. So we actually all the time have two networks which are overlapping. This, let's say solutions of the networks are overlapping, and the sum of those two, for example, will in the end give us the solution. And actually we only do the global optimization via a gradient-based method. So this is very close to how you would in a standard way train pins. And this is really introducing an additional iteration. Okay, so I first want to talk about this more classical approach with the Schwartz iteration. And I'll be talking about this deep DDM method, which has been introduced a few years ago, where basically, well, you have a pin on each of the domains, and you solve the PDE on each domain. So you have here, this is again the residual loss, and B, so here the residual loss are the crosses in the plot. You have this second loss term, which is basically the boundary loss, so enforcing our boundary conditions. So these are these diamond shape sampling points. And we have this third term, which are these circles, which are basically the points where we enforce transmission conditions. So for example, here you could think about you trying to minimize the deviation of the actual values of a Dirichlet condition on the boundaries. And then there is basically a local part in this iteration where you train your local networks. And then there is a global part, or let's say at least a communication part, where you communicate these values between your different subdomains and update these interface values. Okay, so this is the first method, and it is also somehow a bit close to what you could do for a non-overlapping method, maybe by introducing some, let's say, those jumps terms at different locations or different types of transmission conditions. And I'll be talking about different types of numerical examples here. And mostly I try to do something similar that I would also do for classical methods, something like strong scaling and weak scaling tests. And it's a bit difficult here in this context to say what is strong and weak scaling. I mean, for classical methods, it's easy because the computation work directly and complexity kind of corresponds often to the number of degrees of freedom. Here it is a bit more difficult to define those terms. So let's say my definition for this talk is that strong scaling, meaning I have a problem of fixed complexity and I increase the model capacity. And I will mostly do that by adding more subdomains. And the other approach would be weak scaling, where I make the problem more difficult and at the same rate give more capacity to the model. So I would increase the difficulty of my problem at the same rate as I would increase the model capacity. In the first case, strong scaling, we would hope that by giving more capacity, the result improves. In weak scaling, we would hope that, well, if we increase both at the same rate, we get similar performance. And now I use this approach that I showed you before, this deep DDM approach. And let's in this case here, it's a strong scaling test. So I take a simple Laplacian here, it's in 2D. And so I take the same equation, I increase the number of subdomains, and I would be hoping that I improve my accuracy, for example, or that I train faster. And what we see is not the case. So here we have there is some inner iteration going on, which I don't show here. So as I said, I solve the subdomain problems, which is an inner gradient-based optimization. And I have this outer fixed point iteration. And something we see here is actually the opposite of what we would be hoping for is happening. So we would like to have more subdomains, better performance. And here you see if you increase the number of subdomains, performance gets worse. So that is not what we would like to do. But this is a phenomenon that is very well known, actually, also in classical methods. And it can be kind of visualized or thought of in the following way. Basically, the unique solution that we get is determined due to the way or due to the boundary conditions. But if you increase the number of subdomains, the boundary conditions are more far away from the most interior subdomain. So the information transport from the boundary to the interior, would be, for example, one outer iteration. The boundary information can only travel by the width of the subdomains, but it can never travel anywhere interior within one Schwartz iteration. And then within the second Schwartz iteration, it can go a bit further, and so on, right? So it takes for information to be transported from the boundary to the interior. And this means the more subdomain I take, the more difficult it will be to, for example, get a good solution in the innermost subdomain. Okay. So this is difficult somehow, but it is something that is, let's say, known how to fix this issue for classical methods. Namely, something that we typically do is we add something that we call a coarse problem, or a second level, which means that we introduce a second, let's say, model or something like that here in the general setting, where which is maybe small, which is a rough approximation maybe of the solution, but which gives us directly in each Schwartz iteration global transport of information. And here in this deep DDM method, you can do this by introducing an additional network that is trained here on these on these square collocation points. So it has collocation points everywhere, and but it's maybe a small network, and so we train it everywhere, and then we do two steps here. In the one step, we ensure that this coarse network U0 is not too far away here from basically a weighted sum of the local networks. Weighted sum in the sense that we have to do something weighting with the partition of unity on the overlaps of those local networks here. So we make sure that this coarse network is not too far away from the local solutions, but then we train the coarse network, and in a second step we give some information back to the local networks. And here we do it in the sense that we in those interface or this transmission terms, we incorporate the error against the coarse network, not just so a weighted sum of the solution of the coarse network and the neighboring subdomain network. And by that, we give some information back from this global transport or global model to the local models. And these blue steps are the additional steps that come in. They are kind of, if you think about it in a really parallel setting, this can be, of course, a parallel bottleneck in the sense that this is one global model that couples everything, right? But it gives fast transport of information. And of course, yeah, there might be other ways of doing this coupling. This is just one way using coupling the local models with the global model. And now just to check what happens, I'll do this now for a weak scaling test. So this is a problem where basically I can increase the frequency of the solution in X direction or in X1 direction by increasing alpha here. Here are all the hyperparameters, which I will not, I will not go through all of them. I will mostly not discuss them in all of the slides. So if yeah, maybe you can just, if you're interested, you can look at them. And but what you can see here, for example, if I would increase alpha, I can have more more oscillation in the X1 direction of the solution. So I can do something like I can make my problem complexity also larger by increasing alpha. Okay. And let's now see what happens if we now do this two-level approach. So here we increase the frequency while increasing the number of subdomains. And something that we notice is that if we don't add a coarse level, again, we have the same issue as before, right? So I take more subdomains and the solution gets worse. And I can, in the weak scaling setting, I can fix this. So I get roughly similar performance for all the models when I add such a coarse problem. So we can kind of fix the scaling issue. Okay, so this is the, let's say, just, let's say, first showing that you can do domain decomposed pin using this classical Schwartz iteration approach. Now I will go to the second approach, which is a little bit different. So as I said, we forget about this outer Schwartz iteration. What we incorporate this domain decomposition just in the neural network architecture and keep training it with a classical gradient-based optimization. Okay, so I will talk about this. Well, it was denoted in the first paper as finite basis physics-informed neural networks. And but it is a very, let's say, very close to a domain decomposition approach. But you can also, in another way, and I maybe come back to that again, you could also see it a little bit as a, well, maybe like an HP finite element where you can also do some age refinement by introducing a domain decomposition, but you also have the chance of making your local ansatz space richer by steering the network capacity of the local networks. So it's kind of one can also see it a bit more in this context, in this kind of discretization context. So again, we start with a generic partial differential equation. In this chapter, I will just to say that already because we found this quite useful in our tests. We always incorporate the boundary conditions as hard constraints. So as in this very old work paper from 25 years ago, here I have this generic operator C, a calligraphic C, which just basically ensures that my network function will satisfy boundary conditions. And there's always a way, I mean, here I will always have full Dirichlet boundary conditions, and typically zero even. So it's very simple to design such an operator that enforces this. We'll not go into the details. So we have a partial differential equation. We enforce boundary conditions as strong as hard constraints. And then this FP-pin approach is actually I would say it's very simple. So basically the only thing is that we change the network architecture. So again, here, this is the boundary condition operator. And then instead of taking one network, what you would do in a vanilla pin context, maybe you take a weighted sum of local network functions. So you have here a sum over the J from 1 to J, capital J, which are the different subdomains. And you have for each subdomain a local network. And why is this network local? It is local because we multiply it with such a function omega j, which is a partition of unity functions. So, and here in the original paper, it was denoted as window functions. So for example, if you think about this blue one, it's a function that is inside of the subdomain, inside of this blue subdomain mostly is 1, and then it smoothly decays to 0 and is exactly 0 where the subdomain ends. And you introduce one of those functions on each of the subdomains, and then of course if you multiply your network with this function, this multiplication gives you a localized function. And because they all sum up to 1, in a sense, you can, let's say, even if you would have the exact solution on each subdomain and you multiply it with a partition of unity, you would get back the exact solution. And something that happens, for example, if you use this approach here, then to train actually the same loss as the standard pin, but now we plug in this, let's say, this decomposed network architecture. Then we get this kind of partition of the solution, right? So you see that the global solution is kind of a sum of functions which are only supported on local overlapping subdomains. Okay, so this is kind of, I mean, this is a simple example, but let's now look at again two other examples. Let's first look at the left part where we actually take this high frequency example that I showed, well, a couple of slides earlier, which was very difficult to train with a vanilla pin. Again, not saying that you cannot do tricks and make it work. But if you just do it in a plain way, it's difficult. But now if you do this domain decomposed neural network architecture, you get really the solution everywhere. And the interesting thing is now really, for example, if you fit the domain decomposition with the frequency, you mostly have to you have to approximate one period of the sine here, which is quite simple. And you see that it converges very quickly. And because you really localize this architecture a lot, and this also allows us to take quite small networks on each subdomain, it is also very, very efficient. And it can be parallelized easily on GPU.
Alexander,
now,
can I ask you a question on this one? Because I think there's, let's use the word overlap with the A pin, the augmented pin that a group from Singapore used, called blending functions, but basically the same concept. So it's a paper that you didn't have in your references before. It's called A pin. It's Zheyuan Hu is the author. There's also rigorous theory that shows convergence and so on. This is from
yeah. No, I'm aware of this.
Yeah.
No, I'm aware.
Can you point out the differences with your method? Since you're 2023 and they did this before.
Sorry, can you say again? I didn't understand.
Just say the difference. What the difference between your method and the A pin?
Well, okay. So I'm aware of the work. I have not looked in that much into the exact differences. So I cannot say exactly at this point.
Okay.
Yeah. So, I'm aware of that there has been this work, but let's say we haven't really done a really detailed comparison at this moment.
Yeah, Ameya, I don't know if you're online. Maybe you can comment.
Yes, George. I need to think. I know both the method FB pins and A pins, but I think they are not they are doing domain decomposition a priori. I mean, whereas in A pin we have to find out the best subdomains to the way we need to decompose. I think that's one of the difference. Rest I need to think.
Yeah.
Alex, this is Suku from Davis. I had a question on the previous slide.
Sure.
Yeah, so actually, what you have shown here, this window function is basically what is called a flat top partition of unity. You might be familiar with it.
Sure.
Work of Melenk and Babushka and things like that, right? Basically. And the other thing is that, how does one generalize this to more complex domains where it's not a Cartesian grid where you can create the flat top partition of unity?
Yeah.
I've been thinking about this for many years now.
Yeah.
But the challenge is really in constructing it on more unstructured domains where it's hard to conceive of a flat top PU, right?
No, so I agree. So good. It's a good point. I'm fully on your side. It's also something that we are let's say thinking about. I mean, has been work on these partition of unity networks by Netrask and, for example, Eric Sear, for example, and which is basically I think, as I understood, mostly the part that I've seen was mostly on let's say really function approximation. I'm not sure. I mean, it might be an idea to think about something like that, but yeah, it is definitely Sorry?
Yeah, because I have written some documents on this a couple of years ago on at least some ideas of how do you generalize it to unstructured or arbitrary domains. But it's of course challenging in general also, right?
Sure.
Because there are other issues also which arise. Because you want a general method and not something only for square and rectangular or cuboidal domains where it's very easy to do it, where most of us have done that work with flat top partition of unity. But generalizing it, given an unstructured mesh or given a finite element mesh, how does one construct this flat top? Because one of the interesting properties, which is what is appealing to me, is that the flat top provides you basically global stability. It provides you global stability, unlike other partition of unity methods. Because because the flat top region, you can show there's linear independence between the basis or the neural network on each subdomain. So that's a nice property to have just by construction, and that's why. But of course, the challenge is how do you construct the omega functions on an arbitrary domain? And benefit, of course, is that you don't have these interface conditions, right? Which you pointed out. And a related paper, which I don't know if you've seen before, on the Schwartz alternating is there's also this work by Irina Tozor, and goes back to classical sort of Schwartz alternating, but she's applied it to, pins actually. And I can dig up the reference. I just remember the paper suddenly. I think it appeared last year sometime, but I can dig up the paper and post it on the chat. It might be relevant to the first approach you talked about, but because there are different variants of alternating Schwartz, right? So it might be just a different variant of that. So that's just a comment. And the other sort of remark I had is when you talk about the interface conditions before, I mean, is there an impact whether you use what type of interface conditions you use? Is it a Dirichlet or a Neumann or combination, or how does that work in terms of does it impact the results? What I meant to say.
Yeah. Okay. So
I have too many questions. I'm sorry.
Yeah. Okay. Maybe I think the first one, if I understand correctly, basically, so let's say short or hopefully short answer to your first question. I think it's an interesting question how to do this. Do it for general domain. Let's say create a general domain decomposition. And of course, if you have a mesh, there is a lot of classical work on how constructing overlapping domain decompositions, right? But if you don't have that, it is not this is not, let's say, it's not a trivial task. It's also not trivial in terms of efficiency, of course, because something that we can do here, like very easily, is distribute collocation points to subdomains or generate randomly collocation points based on the domain decomposition. But once once it's more irregular, let's say, it is not that is not so, you cannot easily do it in such an efficient way. I agree. It is a topic that needs to be investigated. I don't have a solution at this point.
Sure.
About the interface conditions, so there is a lot of work on classical domain decompositions on which transmission conditions to use. I mean, there's like a whole class of methods which is called optimized Schwartz methods, where you do where you take, let's say, more Robin type boundary conditions in order where you can get improved, for example, improved convergence by using other types of methods. And for example, if you look at wave problems, and I will later show a problem where you see, so we haven't improved it yet, but you will see that our method actually suffers from the fact probably that we don't use the right boundary conditions. So for wave problems, it's kind of it is known that Dirichlet is not a good choice, for example. So it is a bit problem dependent. The more you know about your problem, the better you can design that. But in what we have shown so far, just let's say to give this algorithmical, let's say introduce this algorithm, it's just a Dirichlet condition.
Sure. Okay. Thanks.
Yeah. Okay. I also just to go quickly back to this A-pin thing, I'm aware of. I think also it is somehow very close. I think there's a bit more flexibility on the domain decomposition, but I don't want to say too much about it because I would really have to go back to that paper to see the exact.
It also has theory, it has convergence, it has rigorous numerical analysis.
Yeah. Okay. Any other question at this moment, or can I? Okay, I'll just go on. And then, but again, now what happens? So the left problem is quite simple here in certain sense. Well, in another sense, it is quite simple because the global component of this solution is zero, right? The mean is zero, so it's not required to so you don't actually need a coarse network or a coarse model for the left part. So you can more or less train all the individual solutions more or less independent of each other. So, and this can be easily seen again by going to a seemingly even easier problem in some sense. So if you again look at the Laplacian here problem, then I mean, you actually you don't have any local features, but just this global feature. And you then see that this one level method again doesn't really work well, right? So you see again that if you increase the number of subdomains, even for such a simple problem, the convergence really deteriorates. So we again have to do something, let's say something more, and similar to before, we will do this by introducing a coarse level. And I mean, this is also kind of maybe the main, let's say, main thing that I'm, let's say, trying to, let's say, show here is this, let's say, the way how the second level or multi-level methods improve.
Can I ask a question? I mean,
yeah.
I mean, that should be expected, right? Because we know to build a preconditioner, you need to have the coarse part.
Sure. Yeah. So it is obvious.
To do parareal, you do the same thing, and so you always need the coarse part, no matter how you do the preconditioner. If you do multi-grid or you do Krylov methods or whatever, you need the coarse part.
Yeah. So it is really obvious. Yeah. So it's let's say kind of it was nice to see that kind of by using similar let's say ideas, you can again, let's say, recover also, let's say, good or better properties by using similar, let's say, techniques or ideas that you would also use in the classical methods. But yes, it's true. I mean, this is for classical methods. This is all very well known. Then we and what we did then, because in this framework it is actually because everything is, let's say, fully additively coupled. It is we can introduce a second level in an additive way, in a quite simple way, but we can also introduce as many levels as we want in a quite simple way without having to change much the framework that I showed before, this FB-PIN framework. So so here I will directly go from one level to whatever L levels. So basically the way I will do this, typically well, one would typically number the levels differently, but in the results that I show here, I will usually start with one level first, which is one global model, and then I will refine. So that is how I would order it. And here I typically do a decomposition in the sense that I always halve I do a coarsening ratio of 2, so I always refine by a factor of 2 from one level to the other level. And on each level, I would have a different partition of unity. But this is of course flexible, so you can, if you have a way, for example, as discussed before, of finding better partition of unity, better domain decompositions, or more adaptive way, there's no reason why you couldn't do this in the same way, right? And then you just have, in addition to having a sum over all the subdomains, you also have a sum over all the levels, and nothing else changes. And these are some, let's say, just some ablation studies for the 2D Laplace. Just to see, let's say, I'll go over this. I also notice now time is running a bit because there was a bit of discussion, so I'll try to speed up a little bit. So there's, let's say, some things that we noticed.
Okay, Alexander, it's okay. You can take your time.
Okay, good. So there were some things that we noticed by doing some of those studies. The first thing is, if we look at the leftmost, so there now you will always see a lot of well, all these figures are very busy. One thing that we always did is we always trained multiple, like 10 models, and then we always show here, let's say, the mean result, but also the min and max, to account a bit for the, let's say, randomness of the initialization and training. And but you still, I think what I mostly want to say again is the qualitative things you notice. Firstly, what you see is if you do one level here, if you add in more and more subdomains, at some point convergence will get worse. Whereas if I do this multi-level thing, I always get to roughly the same accuracy. Of course, in this model, to say that, I mean, here you would never do more than one pin probably. Right, because this is, for this problem, there's no reason to do multi-level, but this is really just to investigate what happens if you change some of the parameters. Also, you see that if you make your overlap a bit wider, this up to a certain point, this improves performance, which is also kind of similar to what you would expect from classical methods. And up to a certain range, we also see that increasing the number of units. Here we always only use one layer for the local models, improves a bit the performance. And here this is the result if you just use a plain pin. Okay, not again. You might be able to do it better, of course. And now we have, let's say I will show two results for two different, well, like this problem is really very artificial. So we really constructed it in a way that we can really nicely investigate what happens. And so we designed this problem where you start with one period of the sine in each direction. And then you, on the next, let's say if you increase the sum to 2, then you would add one sine in each direction with twice the frequency and so on. So it gets kind of, yeah, you get exponentially more periods of the sine, and you add all these together. And now, but if you think back about how we did this multi-level domain decomposition, we can, for example, if we do one subdomain here, we have one pin that has to approximate this solution. And then if we add 2 by 2 pins on the next level here, again, each of those additional pins only has to basically approximate one period of the sine and so on. So we can basically choose the domain decomposition such that it fits nicely with the problem structure. And then we can investigate nicely what happens.
And I was wondering if the, Suku here, just a short question.
Sure.
If the frequencies are, if the high frequencies are not aligned along the X and Y axis but are inclined, basically a wave coming from a different direction, then how does it perform? Or do you do the domain decomposition the same way, or do you align it with the, where it's coming from, the direction?
If you know your problem structure, of course, the best way would be to align your domain decomposition with the way the solution is structured. As I said, this is really more, I mean, this was really designed such that we can nicely see, let's say, maybe the best case where we really know this. Of course, we should at some point do much more studies about this.
Yeah, because in a typical, if you give it's like to draw a comparison with a finite element case, right? Where you have a given mesh, which is very fine, but it doesn't care. I mean, in some sense, the forcing function does not matter, right? You'll get the same accuracy, ballpark, right? So that was the thought.
No, I mean, you can, of course, let's say if you use a lot of subdomains, it will probably still be good, right? Because at some point you will be able to approximate this well, but I mean, the more you know about the problem structure, the less you need to refine, maybe.
Yeah.
Okay, so now quite some results about this. So firstly, this is dimensionless strong scaling. So we take the most difficult problem here, and if we first look at FP pins, we increase the number of levels. And these are the different shades of blue in this plot. And you see that the more, let's say, the more levels we add, the more we get to the actual correct solution or to the exact solution. We tried a fine pin, vanilla. It didn't really work that well. We also tried a pin with Fourier layers, Fourier features as an input, and self-adaptive pins. And they all, I mean, Fourier layers here worked a bit better, and the self-adaptive pins didn't perform that well. And in addition to do that, we also did FP pins with a more, so this is just one level. It is worse, but here still works quite okay. And this is FP pin with a more coarsening, and this also performed, let's say, quite reasonable. So we saw that, firstly, that we can improve, against, let's say, some of the methods we compared against. And also we generally have let's say, a nice, efficiency here because, because we have this parallelism. So, and then we did also weak scaling, where this is now just for FP pin, where we, at the same rate, increase the complexity of the problem as we increase the model capacity. So we increase the complexity as we increase the number of subdomains. And in the ideal world, all of them would be going to the same accuracy, which is not the case here. So this, we don't have a perfect weak scaling, but in all cases we get a reasonable approximation of the solution. And we can also see that it takes more time to approximate well. Okay, then last problem results for this type of model is for a Helmholtz problem. And this comes back to the question that I heard earlier, where now you will see, that we didn't do this in the best way. And we don't get especially for this right case where we have a high wave number, that our model does not really perform very, let's say, perfectly yet. Okay, so firstly, these are just some plots of solutions with different methods. So we increase here the complexity of the problem, and I use the different types of methods. With FBPIN, we first are quite good. For the highest frequency problem, there's also a significant difference actually to the true solution. But we see that all of the methods have quite some problems with approximating the highest frequency case. And if you then also look at these errors, you actually see that for, let's say, up to a certain problem complexity here, we still have, let's say, maybe reasonable results. But then if we go to the really high frequency problem, you really see that they all kind of, not completely fail, but kind of fail. So there is, let's say, one thing, without, again, taking the whole Swiss Army knife of pin techniques that you can do, let's say, just thinking about the domain decomposition, one thing that I could think of is using different ways of transmission conditions, because it's well known that for wave problems, pure Dirichlet is probably not the right way to do, the best thing to do. Okay, last thing. I mean, I still have this last topic. I hope it's still fine. Maybe in the end, there will be a little bit less question because there was already some discussion in between. So this is now going to time-dependent problems. So this is combining domain decomposition with multi-fidelity stacking pins. And now we do actually domain decomposition in time. Okay, and just to, let's say, set the stage for this type of method, I'll just start with first observing what happens if you train a pin here for a simple pendulum problem. If you, here in this case, if you train it, plain vanilla pin for a short time range, 0 to 4, you see that it works quite well. If you try to train it for a very long range, at some point it gets at least, let's say, more difficult to get, let's say, to get the whole solution over the domain. Then there has been work by Amanda and Panos and co-authors, where they introduced this stacking multi-fidelity approach, where basically you first train, let's say, a first model, and then after you do that, you train, let's say, a second model that is, let's say, kind of a correction of the first one, but you always train with the, let's say, basically based on the same physics-informed loss. And basically, to the first model, you add a linear model that learns a correlation between the first model and, let's say, a second nonlinear model that you use in order to basically correct for the first one. Again, there has been a lot of work on let's say, these, let's say, related approaches, and I'm sure I don't have everything in the list here. And also there has been work in the, let's say, in the field of operator learning. So there's already quite some work. Something that we wanted to do is combine this with, let's say, using this as the course model, and then increasing, let's say, on each next level, we use a domain decomposition to make sure that on the next level we can approximate the more fine-scale features of the solution. Okay, so but first, let's just see what happens if you do the stacking approach for this model. So if you're in the first step, if you train different pins, you always see roughly the same behavior. You get maybe get the beginning quite okay, but then you don't get the solution on the whole global domain. And the more of these stacking, let's say, levels you add, the more you are able to approximate the full solution. Okay, and here these are just different runs with the, let's say, similar type of model. So you can, using the stacking approach, you can get the solution on the whole domain. And now, as I mentioned, I will be mostly talking about the domain decomposition aspect of all this. We make this, we combine this idea with the domain decomposition, so with this FB-pin model, where we first train this pin on, let's say, one pin on the global domain. We correct it in the stacking sense by two models, which live on two parts of the domain, from the first part of the time, second part of the time. And then we combine this and correct this again with maybe four models that correct on different parts of the temporal domain. So it's kind of, we do like a refinement. And one should say that this is really trained in a fully sequential way. So we really train this first, freeze it, and then train the second level, right? So it's a bit different in the terms of the coupling compared to the previous approach, where we train everything in an additive way at the same time. Okay, so this is the approach. And now I'm almost done. So I just want to show some final results about what happens if you do this. So this is, again, this pendulum problem where actually you kind of have the same frequency throughout the whole domain, right? So it's kind of, we see if we use this FB pin, so this domain decomposition approach, we see that in the beginning, let's say we reduce the error a bit quicker, and we are a little bit better than if using the standard stacking approach. But here I think the improvement is still quite moderate. So we see that, for example, if you compare this stacking pin with the FB pin stacking approach, we see that we get a better error with less parameters, actually. So if you, for example, compare this model with the model that you would get here with the stacking pin, so 2 levels of FB stacking with 4 levels of standard pin, which have roughly, let's say, comparable errors, we can get, let's say, even a better error with less parameters, which is kind of nice. But then second problem where this actually, where you see this even, let's say, even more pronounced is once you take a problem where you have 2 frequencies in the solution. Of course, you could, in the same way as we designed this problem with multiple scales before in space, you could also design a problem where you have even more different frequencies, of course. But now you see this even more clearly, right? So if you look at just at the plot here on the top, you have all the details again. If you look at this dashed line, you see what happens if you do train 1 pin as an example. If you do the stacking pin, you are definitely much better. You're getting much better after a certain number of levels. But then if we use this, combine this with the domain decomposition, we are more easily able to approximate the fine scale features. And by combining this, let's say, the stacking with the domain decomposition, we can get very good accuracies with, let's say, relatively low numbers of parameters, for example, here. But then, of course, you can, if you add a lot of those levels, and of course, on each subdomain, we have 1 network. So this can go to a very large model at some point. But then we can also really get low errors. And this brings me to my finally last slide. And then I really took the whole hour, unfortunately. This is a last result is showing what happens for the Allen-Kahn equation, where what you notice, and this has been seen in some, let's say, some works, is that if you train a single pin, you often run into this fixed point of the dynamical system or stationary point here, which is also, if you cut this here vertically, it's basically this blue dashed line. So this is often the solution you run into if you train a single pin. But then if you add this with a domain decomposition approach, you're actually able to recover the full, let's say, the correct solution very well. So we think that in this context of the time-dependent problems, even then it can be very beneficial to combine this multi-fidelity with the domain decomposition approach. And as in all the things before, of course, the more you might know maybe about how to do the domain decomposition best in an adapted way to your problem, or if you can even adapt it, yeah, then you might be better or worse. Good, and this brings me to my last slide. Well, I hope everything was clear. We'll just leave it like that and not read it all out. I hope this story was clear. Thank you very much for your attention.
Thank you so much for your great talk. Now we open the floor for questions. Do we have any questions from the audience for the speaker?
I have a question, Alexander. Actually, there's, I mean, I'm sort of following the literature, and I see a lot of misunderstandings. Let me clarify one, for example, for the last one, for the Alan Kahn. The Alan Kahn, if you have self-adaptive weights or residual tension-based weights, you can solve this problem in a jiffy. Even standard, if you play with the weights in the loss function, it is standard without fixed weights. If you run long enough, you actually get the problem. And we're about to come out with a paper that explains how pins learn, the theory of learning. So that explains everything. So, but I was wondering why you didn't. I mean, you made lots of comparisons, but not the comparisons I would have made, because X-pin and C-pin were developed a long time ago. So X-pin, for example, can do both time and space discretization, but you didn't compare with X-pin. Was that intentional, or you didn't have the code?
No. So I mean, of course, but let's say, of course, you have to make, let's say maybe the first thing that you said is you can add some, let's say, techniques to make this better, and of course,
no, not techniques. It's very fundamental. I mean, it's not like a trick or Swiss knife that you mentioned.
No.
It is very fundamental for learning, and that's why I say there's a theory of learning, which is associated with the self-adaptive weights, the adversarial training of pins, but also the local, which corresponds to frequencies. Actually, turns out that these weights corresponds to frequencies and local wave numbers that you're resolving. So
for example, in the one work we compared with self-adaptive, for example. But I mean, of course, you can also combine this with self-adaptive weights, right? So I'm not saying, I mean, I would not say that this is the one versus the other. But in a sense, because you can, of course, use these things together. I mean, it makes a lot of sense to combine these things with the domain decomposition, right?
But you work with Mishra, and Mishra work on X-pin. Why you guys didn't compare X-pin versus for any of these problems?
Well, as I said, we were the initial idea was to compare with, let's say, vanilla pin, and then, as I said, we compared with some, let's say, added some of these things like Fourier features and the self-adaptive. I mean, maybe we should also compare against X-pins. We didn't do it at this point. There's no specific reason.
Okay, and another clarification. Which I see that is sort of propagated like fake news. It turns out that when we did the pins in 2015, 2016 timeframe, when we were working on pins, we had no clue about the Lagares paper. The Lagares paper surfaced later by a reviewer that told us. That's why in the archive paper we didn't have it, but in the paper we have it. But if you look at the history, the Lagares paper is 4 years later than the paper by Fan Tien. Fan Tien is very famous for his polymer model, Fan Tien model. But anyway, Fan Tien in 1994, in one of the non-Newtonian fluid mechanics journals, published exactly this, the collocation method for the full polymer non-Newtonian equations. So the Lagares came much later in a much simplified form. So if credit should be given to Fan Tien.
Okay, well, good. I mean, thanks for pointing
that out. You can see that this different than pins. Pins we were targeting at the time. It was an uncertainty quantification project. We're looking at data, so we're targeting data. But so it's I mean, I know Lagares and Fotiadis and all these people, and they're good people. But what I'm saying is the origin of this idea goes back to Fan Tien, and that's the paper that one should actually 1994. You can find.
No, thanks a lot. I'll take a look at it. I was not aware of that. I think I also made I think it's really the point that this data point. I mean, that's clear. This is really the
data point, and also the fact that the neural networks are differentiable, so you can use automatic differentiation, because before that they were using Still-Taylor expansions for the operators. So there's these two issues, but I see a lot of people who write the history of pins. They propagate fake news. So somehow somebody has to say that Fan Tien was the guy to get credit.
Okay, no, it's good. Thanks.
Before 2015 is due.
Okay.
But
thank you. Do we have any other questions for the speaker? So I don't see any other question. Thank you for your great talk. It's time to close the first session, and we will move on to the next session with another speaker. Matthew, can you hear me?
Yes, Nazanin, I can hear you fine. Thank you very much for the kind invitation again.
Yeah, welcome. Can you share your screen to see
Yes,
if there
of
is
course. Let me see. All right, can you see the slides?
Yes. And now I will start introduction. Okay, our next speaker is Matteo Salvador. He will be giving a talk on physics-based and data-driven methods for precision medicine in computational cardiology. Matteo Salvador is a postdoctoral researcher at Stanford University working in the cardiovascular biomechanics computation lab under Professor Alison Marsden. His work focuses on computational cardiology, blending physics-based modeling, numerical methods, scientific machine learning, and uncertainty quantification. Salvador holds a bachelor and master's degree in mathematics, mathematical engineering, and computational science from Politecnico di Milano. He earned his PhD there too, contributing to the iHeart project for simulating cardiac function under Professor Alfio Quarteroni. Matteo Salvador also spent time as a visiting student at Johns Hopkins University and later as a visiting researcher fellow at King's College London. With that introduction, the floor is yours and you can start your
Nazanin, let me
presentation.
also congratulate Matteo because their paper just became the best
Yes, yes. I actually got the
sustaining
news
paper out
today.
of 200. After 200 candidates, their paper on heart with Alfio Quarteroni, a good friend, the big team, deservedly won the #1 best paper of the first ever, the inaugural Hughes Orden Award. So congratulations, Matteo.
Thank you very much, Professor
Congratulations.
Kanedakis, and thank you, Nazanin, for the very kind introduction. And good morning, everyone, again, of course. So in this presentation, I will try to give you a broad overview spanning my PhD research and my postdoctoral experience, ranging from activities at Politecnico di Milano in collaboration with King's College London and here at Stanford. And as Nazanin already said, my research is kind of at the intersection between physics-based modeling and data-driven methods for precision medicine in computational cardiology. In particular, I would say that these are the three main pillars my research is focusing on. On one side, you have all the important cell and organ scale physics-based knowledge that you can leverage from experiments by extracting rigorous partial and ordinary differential equations describing the cardiac and cardiovascular function. And once you actually adopt suitable numerical schemes, nowadays we can really perform very comprehensive cardiac simulations using high-performance computing. As everybody in this room is certainly aware of, in the past few decades, thanks to the advent of several artificial intelligence-based methods, we can finally leverage these high-dimensional data coming from physics-based numerical simulations, especially using neural networks, to build accurate and efficient surrogate models that then enable sensitivity analysis, robust parameter estimation, forward and inverse uncertainty quantification, using a very small amount of computational resources, and by providing answers that are compatible with the clinical practice, which is very, very important. So very short time spans. Hopefully in the near future, and this is actually true also for other fields of engineering, we will hopefully envision digital twinning, where for computational medicine, what I think is necessary is to have a continuous bidirectional interaction between mathematical models and clinical data, computational pipelines that are fully integrated with the clinical practice to perform patient-specific assessments for personalized treatment and surgical planning. During my PhD under the supervision of Professor Ralph Quarteroni, I was involved deeply in the activities of the higher project. And here in the bottom, you can see some of the papers coming out from this project. And the idea was to build the most comprehensive model, multi-scale and multiphysics model of cardiac and cardiovascular function available in the literature. Starting from the left, we have a very simple lamp parameter network representing the atria, which are the upper chambers of the heart, and the ventricles, which are the lower chambers of the heart, together with the systemic and pulmonary circulation by means of simple electric circuits in 0D, so 0D elements here. And then step by step, we added the 3D features to the model by considering a fully coupled cardiac electromechanics in the biventricular part of the heart, and then going to full-fledged 3D whole heart electromechanofluid simulations. Here, I'm just trying to give you an idea of the complexity of the mathematical models behind these multiphysics and multiscale formulation. We have several sets of PDEs and ODEs that are acting at the cell level and at the organ scale. Electrophysiology is highly nonlinear. We have a wavefront propagating throughout the computational domain of interest that we want to capture. We have active mechanics because the heart is able to autonomously contract thanks to the stimulus that is triggered by the nervous system. And we have an active tension that is generated throughout the cardiac cycle with an active force. And then we have the coupling with passive mechanics, very complex boundary conditions at the epicardium of the heart to account for the pericardial sac, the interaction with the surrounding organs, and other boundary conditions to allow for consistency in the energy formulation in the 3D/0 decoupling. In the higher project, we developed several novel numerical schemes and mathematical models, also in the framework of multi-patch isogeometric analysis, spectral element methods, matrix-free high-order methods to allow for this type of numerical simulations that you see here, where we simulated the physiological cardiac function with an unprecedented level of detail by matching for the first time many biomarkers of clinical interest. And everything has been implemented in the LifeX C++ high-performance computing library, which is the main product, I would say, coming out from the higher project. So this is just to say that, of course, nowadays there is a big hype behind machine learning, of course, but physics-based modeling is very important. I strongly believe that fundamental laws are still very, very important, and developing standard numerical methods is still fundamental. But now, going a little bit deeper into scientific machine learning, I want to present this project in collaboration with King's College London, in particular with a group of Professor Steven Niederer and the Medical University of Graz, where we develop a computational pipeline to enable real-time four-chamber heart electromechanical simulations by properly leveraging latent neural ordinary differential equations. So the idea is basically the following one. We, starting from top left in this sketch, we actually run lots of high-fidelity simulations, 3D/0D closed-loop numerical simulations, spanning a huge parameter space encompassing electrophysiology, mechanics, hemodynamics at the cell level, and at the organ scale. Once we have these dataset at our disposal, we encode the dynamics of some biomarkers that are fundamental from the clinical practice. And I'm particularly referring to the pressure-volume relationship in the 4 different cardiac chambers during the cardiac cycle. And to do that, we basically want to train a set of latent neural ODs to encode the pressure-volume temporal dynamics while spanning this huge parameter space of this multiphysics and multiscale and nonlinear mathematical model. Once we have this surrogate model at our disposal, we can run a global sensitivity analysis, a robust parameter estimation with uncertainty quantification. And once we are confident with that, we can feed the parameters back to the 3D model to have a full-fledged simulation while accounting for all the possible space-time processes behind that. Here, I really want to thank Marina Strocchi, actually a postdoctoral researcher in Steve's lab, for running these huge amount of numerical simulations and for generating this beautiful visualization on the left, actually, of how the displacement evolves in these geometries. And here you can see also a representation of the electrophysiological map behind this patient. But the focus of this work was mostly on all the pressure volume loops that you can see on the right that we generated with this mathematical model. And now going to the scientific machine learning part.
Matteo, how many simulations, how many full simulations did you run?
So as you can see here, we actually ran 400 plus simulations, so 400 for training and validation, and then more for testing, actually, while spanning 43 model parameters of the cardiac and cardiovascular function.
Right. But you only are you saving the full fields, or are you actually, because it seems to me you left out a lot of data. You could use neural operator. You could have the full 3D instead of just these markers. Is it? I mean, your experience, but what I'm saying is that you can be more ambitious actually using these 400 simulations.
Yeah, I actually totally agree with you. So this was like a first step. As you will see, it was already very complicated to do something like that on these geometries. But I agree with you that in the future, we will certainly exploit the displacement, electrophysiology simulations, active mechanics, and everything.
I think there is a Barcelona Supercomputer Center, a group there that they've been pursuing that, because they contacted us like 2-3 years ago about, and they already had in planning the, but I don't know, I'm not in this domain, so I didn't follow what they finally did, but they did have this idea of using DeepONet to do that type of, but 400 is a lot of simulations, so you can learn a lot.
Yeah, I totally agree with you. I think that you are referring to the group of Mariano Vasquez, actually. One of my colleagues from Politecnico, Alberto Zingaro, is a research scientist there, and I know that they're going in that direction as well. So hopefully in the future, we can actually join forces together to really get the best out of these digital twins. But I totally agree that this is the future direction that we have to take for 3D, temporal, and space dynamics using different kinds of neural operators. But actually, going back to what we did in this specific project, we focused on the pressure-volume relationship, temporal dynamics only, which is already very important and fundamental for the cardiac function. And the idea with latent neural ODs is that you have a fully connected feed-forward neural network, a very simple one, that you place at the right-hand side of a set of ordinary differential equations that you want to build, where this vector z of t contains some physical variables, such as the pressure and volumes in the different cardiac chamber over time, plus some latent variables that allows to enhance the dynamics and to stretch the trajectories that you learn for this set of ordered differential equations. Here, as you can see, the neural network receives as input the vector z of t itself, and we have a kind of positional encoding here to account for the periodicity of the sinus rhythm when you have the cardiac cycle and the heartbeat period THB with the cosine and the sine terms. As I was saying before, this vector theta contains 43 model parameters. And we have, of course, a curve of dimensionality issue because we just have 400 2D0D electromechanical simulations that were already very challenging to generate, as we will see later on. And we want to span 43 model parameters and make sure that we get good generalization errors. To do that, we noticed that minimizing the standard mean square error between predictions and observations in the normalized sense, so the first part of the loss function, was not sufficient. We also had to add some a kind of weak penalization of the semi-H1 norm, the first order time derivative, maximum and minimum values attained by the neural network with respect to the observations. We also weakly impose a regularization in the latent space to have periodicity also in the latent variables in case they are necessary. And as you will see in this presentation, I'm a big fan of very parsimonious neural networks like tiny machine learning that is very expressive. And we also impose a weak penalization of the weights and biases here. We perform Clifford cross-validation using automatic hyperparameter tuning so that we don't have to find ourselves the optimal configuration. We use the Bayesian optimizer, the tree structure parts estimator, with a scheduler based on the asynchronous successive alphin, which basically drops out from configurations that are not suitable since the very beginning of the training. And of course, feel free to interrupt me at any point if you have questions. I see a hand that has been raised, so I'm not sure.
Yeah. I was just in the bottom right, it looks like the network is learning the flow map of the system, but the top looks like the thing you're learning is the right-hand side. Which is it that the network is actually the artifact that you take away?
So yeah, the idea is that you start from the initial conditions, and the neural network, you feed continuously the different time steps in the neural network using, for instance, forward Euler. So in this way, you actually learn how to proceed from time step 0 to time step to the final time step THB by continuously fitting the trajectory and do back propagation in the whole simulation, basically, when you do training.
A neural OD with an Euler template.
Yeah, exactly. And here you can see some results. So in the table on the top, you have the different regions for the hyperparameters. And then you have the final configuration that was actually picked by the optimizer. And as you can see, we were able to encode such complex dynamics using a very lightweight neural network with 3D layers and 30 neurons per layer. We test our approach on different data sets with different ranges. And here you can see actually the match between the 2D 0D simulation and the artificial neural network-based method on 5 examples. And the errors that we are obtaining were in the order of 2 to 3% for the normalized root mean square error for pressures, and 3 to 6% for volumes, which is pretty good for clinical applications where the error, if we are lucky, is normally around 10%. So we were pretty satisfied with the results that we were getting here. And even if we are not encoding the whole dynamics, as Professor Kanedakis was actually mentioning, we can really do a lot, even by using these simple surrogate models. For instance, we can unravel by a global sensitivity analysis many mechanisms between model parameters and different quantities of interest, which are the rows and the columns, respectively, of this table in this huge multiphysics and multi-scale mathematical model. Here we are plotting total effects of all indices so that we can account for first-order and high-order interactions between model parameters and QOIs. And some results were pretty expected. For instance, many parameters at the cell and at the organ level for atrial function are actually affecting atrial outputs, and similarly for ventricles. But there are some important exceptions. So, for instance, we saw that the resistance of the systemic and pulmonary circulation, as you can see in the bottom here, is affecting and contributing a lot in determining all the different QIs throughout the cardiac function. And if you look at this specific area of the table, we see that there are many parameters at the cellular level of the ventricles that are impacting the function of the atrial. So these type of mechanisms cannot be unraveled unless you run this global sensitivity analysis because of the high nonlinearities of the model. You really need this type of tools to understand what's going on. And this is also useful for pharmaceutical therapies and for drug development, because if you know how to act on certain cellular quantities in the ventricles to modify the cardiac function at the atrial level, of course, you can get these type of insights that are very useful in computational medicine. And once we know how we can identify model parameters, which is the level of identifiability of model parameters, we can start running some kind of pipelines for parameter estimation and uncertainty quantification. We develop a pipeline again that is able, providing some time-dependent quantities of interest, such as volumes and pressures in time. We are able to extract many more parameters with uncertainty with respect to the amount of quantities of interest that we provide to the model. And we can do that even by estimating quantities at the cellular level in atria and ventricles, including electrophysiology, mechanics, and hemodynamics. Here we consider 4 different test cases with an increasing level of complexity. we initialize our algorithm using a maximum posterior estimation to find an initial set of model parameters. And then we run Hamiltonian Monte Carlo to actually compute the posterior distribution. Here, I'm plotting the bidimensional cuts of the posterior distributions for the different test cases and for some different numerical simulations where we tested our approach in silico, where we had the ground truth of model parameters and time-dependent QIs that we wanted to match. And as you can see here, the black dot, which represents the ground truth, is always contained within the 95% credibility region of the posterior distribution. And this approach is really fundamental also to capture relationships between model parameters that are not given for granted. For instance, in this subplot, first row, third column, you see that the systemic resistance is negatively correlated with the calcium dynamics at the ventricular level. And you can also have multimodality in the posterior distribution, of course, because the mathematical model is very complicated again. And in this way, you can really explore from a clinical perspective these different scenarios with different uncertainty when you want to match model parameters.
So this is fitting the parameters of your neural OD with instead of just minimizing the loss, it's Bayesian.
Yes.
Posterior estimation of those parameters.
Yes, exactly. And so in conclusion, what we developed in this framework was a very comprehensive surrogate model of cardiac electromechanics and cardiovascular hemodynamics using latent neural ODs. We have a very lightweight system of latent neural ODs, which allows for faster than real-time 4-chamber heart electromechanical simulations. And the overall speed up is pretty massive, as you can see from the table on the top. Running a single simulation for 5 orbits on 500 cores, more or less, it takes approximately 6 to 7 hours of computation. So if we would have run a single instance of GSA and a single instance of parameter estimation with UQ on the same amount of computational resources, it would have required 5 centuries of computations. On the other hand, if we are willing to pay the price to generate the training and testing set using the same amount of computational resources, which still is a very difficult technological challenge, even nowadays with the amount of HPC that we have and requires a few months of computations, then training the reduced order model on 1 core takes 10 hours. GSA and parameter estimation with UQ can be carried out again on 1 core in just a few hours of computations. So this is basically the type of results that we were able to get. As a future development, we want to encode different anatomies and different pathological conditions within the neural network, because at the moment, this surrogate model is geometry dependent, is kind of patient specific. But in the future, hopefully, we can envision a universal heart simulator which encodes several patients at the same time, so that we don't need retraining. And if another case, which is a little bit on the edge, comes and enters like a clinical pipeline, we can include that via transfer learning, and we don't need to retrain the reduced order model multiple times. Going to the project that I'm working on at Stanford in Alison Marsden lab, what I would say is that the focus of the lab is strongly on congenital heart disease for pediatrics patients. So here I built together with colleagues, Fan-Wei Kong, Matthias Pelling from TU Delft, Dave Parker, clinicians, Harry Chubb, and Anne Dublin, a digital twinning pipeline of just cardiac electrophysiology for now, as this cohort of patients is still not very well investigated in the literature for congenital heart disease. Among all the possible congenital heart defects that we have out there, one of the most challenging and rare is actually hypoplast left heart syndrome, where with respect to a normal heart here on the left, an HLHS patient has a very small left ventricle with a very small mitral valve. It normally has atrial defects, so there is a hole physically between the two different atria. And these conditions, as I was saying, is very rare. Normally, patients undergo 3 reconstructive surgical operations, and they have a long follow-up care since they are toddlers. And the standard of care is definitely not defined for these patients. There is lots of uncertainty in how these patients are treated from the clinical perspective. And clinicians as well strongly believe that computational medicine can provide some important insights to improve standard of care. My colleague Fan Wei Kong, a postdoc at Stanford in the Marsden Lab, developed a fantastic pipeline using generative AI to pass from image segmentations down to meshes that are ready for finite element simulations, training this deep neural network based on sign distance field, in which she encoded several congenital heart defects, so she's able to segment pediatric patients with different type of diseases. And she's actually able to provide a mesh that is ready for finite element simulations. And then once we are at this point, we can actually run the electrophysiology simulation. If we have the torso of the patient, we can place in silico 9 leads to simulate 12-lead electrocardiogram, which is a standard clinical exam that probably all of us has done once in a lifetime. And here on the right, you can see an in silico generated 12-lead electrocardiogram, where you see that the dynamics is pretty sharp, very sharp gradients. We have a first part called the QRS complex, which corresponds to ventricular depolarization, followed by a plateau, and then a second wave called the T wave, which corresponds to ventricular repolarization. And again, what we did here was focusing on one patient. We ran several high-fidelity simulations using high-performance computing, while spanning cellular to organ level parameters for cardiac electrophysiology only in this case, as it was already complex enough for this cohort of patients. And we are varying calcium, sodium, potassium pumps at the ionic level, conductivities at the myocardial level, and the level of the synchrony between the Purkinje network of the left ventricle and the right ventricle, which is the network at the endocardium of the 2 different cardiac chambers, which is actually providing and triggering the electric signal in the cardiac tissue. Here on the left, you can see the envelope of all the possible simulated ECGs while spanning these model parameters. And you can see that the clinical recordings that we have readily available for these patients are actually contained within this envelope of numerical simulations. And then to encode the dynamics of these 12-lead electrocardiograms, we came up with another tool that we named the branch neural maps to actually build the fast and accurate surrogate models in this framework. And I'm going to explain briefly the idea behind and which are, of course, pros and cons of using this type of tool. So the idea is that we have a partially connected feed-forward neural network where we separate fluxes of information from input to outputs coming from variables with a different intrinsic roles. So if we have the temporal variable, we have physics-based parameters. We can even have space coordinates, for instance, if we want to use them with PDEs. We have separate branches from inputs to outputs. And one of the tunable hyperparameters is actually the level of disentanglement that we enforce, which can be limited to the first hidden layer, or it can go down to the very last hidden layer. And then in order to recover not just one output, but potentially a field with multiple vectorial outputs, we have a fully connected feed-forward neural network at the end to reach the physical space. On top of the physical outputs that we want to model, we can enhance this network with some latent outputs that, again, are ameliorating the dynamics that is learned by this neural network. And here I'm reporting some considerations that we were able to obtain for this case. So if we train, if we do hyperparameter tuning and we fix 9 outputs, so we just use physical outputs. These were the mean square errors for training and testing that we were able to get, which are fairly good for training, but not for testing. But if we do the same by adding latent outputs, we can increase the performances in the training and in the testing set in terms of mean square errors. And of course, at a certain time, we hit a plateau, or we can even increase the testing errors because of the usual trade-offs between the dimension of the neural network and the dimensionality of the training set, because the landscape of local minima can become rough at a certain point. Because one of the ideas of branch neural maps is that by enforcing sparsity, as it's done with spiky neural networks, liquid neural networks, or neural circuit policies from MIT, we are also able to get a landscape of local minima, which is better, where optimization can be performed faster and easier with respect to a fully connected neural network. And if we plot the latent output in time for different instances of the training or testing set, of course, the latent variable lives in a high-dimensional space. And as you can see, it's basically flat for the whole dynamics, except for the QRS complex and the T wave I was mentioning before, where given the sharp gradients, you need an external source that is actually helping you with the training. And another property that we found out using this tool by training them for a huge amount of epochs using deterministic optimizers is that if we sample the electrocardiograms during training with a fixed time step delta t of, for instance, 5 milliseconds, and then during testing, we consider different time resolutions, coarser or finer, the training and the testing errors basically remain comparable for the different instances. So for instance, if you look at 3 different leads here, 1 AVF and V2, for 3 different delta T's, a very fine one and a very coarse one, we see that the branch neural map is always able to recover the in silico electrocardiograms regardless of the time resolution, which is a very good property that we were able to enforce from this very lightweight neural network. Here we are talking about a few hidden layers and a few neurons again per layer. Finally, by considering data sets with an increasing number of simulations, we see that we kind of break the curse of dimensionality, because just with 100 simulations or even less, we are able to obtain a very good training and testing errors. And we are spanning 7 complex model parameters in this multi-scale model. And branch neural maps actually work for now pretty well for in-distribution generalization. So they are not able to perform time extrapolation or these kind of things, but we are working on that to enhance these features. And the training time scales linearly with the number of simulations. And here, basically in 2 to 3 hours on a single core standard laptop, we are able to train this type of surrogate models. Here you can see an example of predictions versus ground truth for different leads. And as you can see, we have a very sharp gradients, a very different dynamics from one sample to the other, but branch neural map is able to capture these dynamics pretty well. And once we have this accurate and efficient surrogate model at our disposal, we can use it again for a digital twinning pipeline. We start by getting a pointwise estimation of model parameters by minimizing the L2 error between clinical recordings and the predictions of the neural network. Of course, we are in a realistic scenario, so we initialize this optimization 100 times or with different trials, with different seeds and different initial set of parameters. And then we average the values that we got to obtain an initial estimation. And from this initial estimation, we can perform an ad hoc patient-specific sensitivity analysis using a Shapley value. So it's a variance-based sensitivity analysis here, where we can evaluate which is the parameter contribution at the cell level and at the organ scale to minimize these L2 error between predictions and observations. And as you can see here, it seems like the cellular dynamics of calcium and potassium is playing a major role, followed by the conductivity at the cardiac tissue level of the Purkinje network and of the myocardium. And it seems like the level of the synchrony between the 2 ventricles doesn't really play a major role in the matching the clinical recordings. And this sensitivity analysis can be performed on a patient-to-patient basis and can vary from different cases, one with the other. And then, again, we perform parameter estimation with associative quantification using Hamiltonian Monte Carlo. We run for different chains with multi-threading. And here you can see the unidimensional posterior distribution over the different sets of parameters, and all the chains are basically overlapping at convergence. As a prior distribution, we use a box around an elder mid pointwise estimation we got at the very beginning. And we assume that the prediction from branch neural maps is actually sampled by a normal distribution centered in the clinical recordings with this covariance matrix, where we have an additive decomposition between the measurement error, which can be actually measured by interacting with clinicians. We were actually able to come up with this estimation by considering the sensitivity of the instrument, the uncertainty in the placement of the leads, the fact that the patient is breathing and there is motion, especially because here we're dealing with a pediatric patient. So of course they don't stay still during the clinical exam. And then we have a second term, which is a Gaussian process accounting for the discrepancy between the full order model and the reduced order model in time. And we have an exponentiated quadratic kernel where we want to match and understand also which is the amplitude and the length scale by imposing additional hyperpriors for these parameters. And we get the posterior distribution also for that. Luckily enough, here we got a unimodal posterior distribution, basically. And the level of uncertainty and the variability of the posterior distribution varies according to the sensitivity analysis that we performed before. So for instance, sodium concentration has a very sharp peak, whereas the level of the synchrony, the TLV stimulation, has a very broad posterior distribution because it's the less identifiable parameter in this game. And when we have the calibrated parameters, we can run again the high fidelity simulation with uncertainty. And as you can see here, the simulation in red is matching pretty well the clinical recordings. And starting from that, we can get the 3D behavior with the calibrated model parameters by just starting from the ECGs. And you can simulate different scenarios of clinical interest pre-operatively and post-operatively for cardiac resynchronization therapy, designing optimal ablation strategies, understanding the impact of different drugs at the cell level and at the organ level, and so on and so forth by using these digital twins. In conclusion, in this section, we develop a tool to encode physical processes using a compact feed-forward partially connected neural network, branch neural maps. We structurally disentangle with branch neural maps inputs with different intrinsic roles, and we have latent outputs to enhance the learned dynamics. We have excellent in distribution generalization and comparable errors on different time resolutions. And for the time being, given the lightweight structure of branch neural maps that we adopted here, in the Julia implementation that is publicly available, you can seamlessly combine during training different deterministic optimizers, such as gradient-free Nelder-Mead, first-order conjugate gradient, second-order BFGS, or even the Newton method. But of course, going to more challenging applications, adding some stochasticity at the beginning with the Adam optimizer is probably necessary. And then we apply this tool to real-time simulation of 12-lead electrocardiograms and for digital twinning purposes. Finally, I just want to give a brief overview of the recent paper that came out on Nature Communications in collaboration with my friends and colleagues from Politecnico di Milano, Francesco Regazzoni, Stefano Pagani, and my PhD advisors, Luca Dedè and Alfio Quarteroni, where we proposed this method called the latent dynamics networks. And you can see here a sketch on the right to learn the dynamics between spatial temporal processes behind the partial differential equations, but this tool is not necessarily limited to partial differential equations. And the idea is basically the following one. You have two different fully connected feed-forward neural networks, a dynamic network and a reconstruction network. The first one receives time-dependent inputs of any kind, which can be initial conditions, boundary conditions, forcing terms, scalar or vector quantities that can be interpreted as constant time signals. And then you have a vector S of t of hidden states, which can be of arbitrary dimension. The idea is that you evolve in time in a neural ODE fashion this vector S of t, and you feed this vector into the reconstruction network together with a space coordinate in 1D, 2D, or 3D domains. And you reconstruct the output of interest, which can be a scalar or vector field from a PD or a post-processing extracted from that to simulate the whole space-time dynamics. And we tested this approach on test cases with increasing level of complexity, starting from advection diffusion reaction equation here, where we vary mu1, mu2, and mu3 in different sets of parameters, and we sample the forcing term amplitude, phase, and the frequency by using different Gaussian processes. Just to report some brief observations, here we are performing a convergence test by increasing the number of training samples. The different dots represent different trials, and the blue line represents the geometric mean in each different instance. We see, of course, that the normalized root mean square error is decreasing with an increasing number of training samples. Similarly, if we decrease the time step delta t that we use in the ODE solver for the dynamic network that we have here, we have that decreasing the delta t is providing convergence in the normalized root mean square error, and increasing the number of latent variables of this vector S of t provides higher generalization up to a certain point. And again, this point can be driven by two different reasons. The first reason is that we actually hit the intrinsic dimension of the phenomenon that we're modeling, so we have a plateau after that. Or again, because of the trade-off between the number of training samples and the dimensionality of the neural network, the landscape of local minimum becomes rough, and we cannot go further in the reduction of the normalized root mean square error. And here you can see an example of space-time dynamics between the full-order model and LDNet for some testing instances, and you can see that they match pretty well. Then we move forward with 2D Navier-Stokes. We consider the lead-driven cavity problem, but not the standard one. We don't put a constant velocity in the upper part of the lead, but we have a Gaussian process in time which can span positive and negative velocities. So we have a continuous generation and destruction of big and small vortices within the lead-driven cavity, as you can see from the movie on the right. And we don't have a quasi-periodic or a periodic regime necessarily. And again, by increasing the dimension of the hidden state, we are able to capture the dynamics fairly better every time we increase the dimensionality of the hidden state. And one of the very important features of the tool is actually this one in the plot on the left. If we compute the normalized root mean square error between the time frame 0-20, and we actually use this time frame for training, and then during testing, we want to see how latent dynamics networks are performing between 20 and 40, we basically get similar normalized root mean square error. So these tools really learn the dynamics behind PDEs while considering a full data-driven model, of course, and we can perform time extrapolation in this framework, even if we are not in a periodic or quasi-periodic regime. And then just to conclude, we focused on a couple of cardiac electrophysiology examples, a one-dimensional one and a two-dimensional one, where we have the monodomain equation with a fixed Nagumo-like reaction term, plus the Aleph-Panfilov model, which is this ODE capturing the behavior in a phenomenological way at the cellular scale. And we actually compare for this one-dimensional case LDNet not only with the full-order model, but with several other tools available in the literature for intrusive and non-intrusive reduced order modeling. In particular, if we look at POD-DAME, which is an intrusive reduced order modeling method, we looked at autoencoders plus LSTM, where we reduce the dimensionality in a latent space with autoencoders, and then we train an LSTM in the reduced space in time. And this training can be done, of course, separately, so autoencoder and LSTM separately, or end-to-end, which means training the whole thing together. And by the way, LDNets are always trained together, so the reconstructor and the dynamic networks are always trained together. And a similar comparison holds for autoencoders plus ODNets, which is very similar to actually autoencoder and the LSTM, but the ODNet also receive the space coordinates as inputs. And as you can see from the plot on the right, the normalized root mean square errors that we got out of that by performing automatic hyperparameter tuning for all these configurations is optimal for LDNets, where we also have small variability among multiple runs. And the number of tunable parameters, again, that are required by LDNets in the optimal configuration is fairly reduced compared to the other approaches. And finally, for 2D electrophysiology, we have bifurcations in the space of parameters. So according to how the signal propagates the second impulse that we provide in the center of the domain here, we can have a focal activation, so normal sinus rhythm. We can have tissue refractoriness, which means that the second impulse doesn't trigger an electric signal. Or we can have arrhythmias, rhythm disorders, which are spiral waves and reentrant drivers that are going throughout the computational domain. And as you can see, again, LDNets are performing very well with respect to the full order model and in comparison to other techniques such as autoencoders and ODNets trained end-to-end or separately. Here I'm reporting some references extracted from the work I presented here today. In these QR codes, you can find on the left the implementation of branched neural maps in Julia and the digital twinning pipeline I showed you on the congenital heart disease patient to reproduce all the results of the papers. And on the right, you can see the implementation of latent dynamics networks from Francesco Regazzoni GitHub repository, together with all the test cases that I've showed you so far. And that's all from my side. I would like to thank all of you for your attention, and I would be happy to take all your questions.
Thank you so much, Matthew, for your great talk. Now it's time for questions. Do we have any questions from the audience for the speaker?
Hi, Matthew. I'm Nikhil. So I'm a graduate student at Brown, and I work with Professor Kardianakis. Can you please go to the slide 5 in second part of your talk? I think you mentioned that you have partially connected network.
Yes.
So I just have one small question. Is it like predefined or the network learns all the time? Like what should be the connections between them?
Yeah, the idea is that differently from using dropout or other type of regularizations, which are more stochastic, you enforce since the very beginning the sparsity that you want in a neural network. This is done also, for instance, in neural circuit policies from MIT, the Matthias Lechner paper, where they have 40 layers with an optimal way of transporting information using cycles within the neural network. They are strongly biologically expired in that case. And by enforcing sparsity, you are really able to get better optimization properties during training.
Okay. So I have one follow-up on that. So is it more interpretable? Like if you look at your outputs to input and you see the network, like the information flow inside the architecture, does it give you more information or something? Like, have you thought about this?
Yeah, I think that the effect of separating flows of information in different branches is more informative and interpretable. And this is actually given here, for instance, because if you consider different temporal discretizations, you can really see that you are really able to approximate the physical process with the same level of, with the same errors, even if the shape of the electrocardiograms is becoming worse and worse. So actually, the neural network differentiated the temporal variable from the cellular to organ level parameters coming from the PD and coupled with the OD.
Interesting. It's great. Yeah, thank you. That's all.
Thank you for your questions.
Do we have any other questions?
Hey, when you talk about digital twins,
Tom, can you introduce yourself first? Yeah.
Yeah, I can say first. I'm Tom Burnham, a research software engineer at UMass Lowell. I do a lot of neural ODE things, and I'm looking at more robotic applications for them. But when you talk about digital twins for these, how important to you is like state estimation? So, a very standard problem in robotics is like a filtering problem where you maybe have a model of some kind for yourself plus the environment, but it's the variables in which it close are not necessarily things that you measure. So you are constantly having to estimate some posterior distribution after whatever you do measure for some state of the system, including like just the map itself, say, for robotic problems. So
I totally, yeah. Oh, please.
Is that important to you at all?
Yeah, definitely. So I think that in the future, we should really leverage these tools. For instance, as Professor Kanadakis was saying before, using these tools or other types of neural operators to learn not only deterministically, but also including stochasticity in the training coming from uncertainty in the surrounding organs, for instance, for cardiac modeling, different types of features, so that we can really account not only for the deterministic state of how a PD should evolve in space and time, but also possible sources of errors since the training of the surrogate model, not just when we do parameter estimation. Yeah, but this is not done so far, but that's certainly a very important research direction.
Yeah, but even if your dynamics are deterministic and how you train this dynamics aside, if you want to run this alongside or something that's actually happening like the heart of a patient or something, is it important to harmonize the state of your model with something that's actually happening in them? Or is it enough to just to get the right class of model that matches them to make some like treatment decisions?
I agree with you. I think that we actually need, on top of what I was saying before, also some kind of gray box approaches in which you continuously update the model and the surrogate model according to the clinical observation that you get. There are some papers in which you train surrogate models at different time scales. So the time scale of the PD, which is a few arbits actually, or the ODE, which is a few arbits, and you couple that with information of clinical exams done by the patient in different moments of his or her life. And in this way, you can have a continuous update of the weights and biases of the neural network according to the information that you get there. And you can account for how the state of the patient evolve through the months, years of his or her life. So definitely these type of tools are fundamental, and they have to be integrated to have digital twins.
Yeah, this is matching like the parameter of the system to the not like the dynamic state of it. As in, like
also the dynamics, like I don't know, you model how the arterial pressure is evolving at a certain freezing the time in the certain moment of the life of a patient. So you train the neural OD on the arterial pressure when the clinical exam was taken at a certain snapshot. Then you redo the exam and you train that on the new arterial pressure that you observe. And in the meantime, you update the parameters and you know how the parameters are evolving of the underlying system of ODs while accounting for this variability. For the time being, most of the digital twinning that is done is a snapshot of that specific condition. But then how to update it in the long run and both in the surrogate model and in the parameters is something that needs to be addressed thoroughly. And we still have to work on that.
Thank you.
Matteo, I have a question on the deterministic optimizers or minimizers, I think you mentioned. I mean, if you look at the information bottleneck theory for learning, unless you have stochasticity, you're not going to learn anything. You're going to fit the data, but certainly you're not going to learn anything. So that's sort of is a two-stage. Actually, we have three stages now. We discovered a third stage, but you do have the first stage where you fit the data up to the point where the but then due to the stochasticity, mini-batch and stochasticity of SGD, you basically wander around, and that's where you do the exploration. That's why you can learn, and that generalization directly depends on this phase, on the exploration phase, which is like a diffusion because of the fluctuation that you have in the gradients. But if you have a deterministic solver, you get stuck there. You want there, you fit the data, sure, but is that learning? That's my question.
So, yeah, that's a good question. And I actually saw your talk at Stanford a couple of weeks ago in which you were explaining this diffusion process from the Israeli professor. And I looked at the YouTube video, and that was really fascinating and interesting. So I think that if you're able to leverage multiple seeds during training, you switch optimizer during training. Because, of course, when you do second order, first order, or a gradient-free approximation, you're actually switching gears in the training phase as well while doing mini-batch. So if you do that optimally for small neural networks, so where the landscape of local minima with these partial connections is not supposed to be super rough compared to bigger networks, I think we were able to do a pretty good job. And we were also able to obtain these kind of discretization invariant framework. But I agree with you that in more complex applications, you really need that stochasticity at the very beginning of training, at least, to be sure that you are exploring the landscape of local minima thoroughly.
But you actually check rigorously to see if you generalize from the case that you did, and you did have generalization, okay?
Yes. Like just to give you an idea, I'm training the neural network on 150 simulations, I think, and I'm checking the generalization on bigger and bigger testing sets that are almost matching the dimension of the training set. So the mean square errors I was mentioning here have been obtained with a data set that is basically as big as the training set, but of course unseen by the neural network.
Okay. And then one more question I have about the last part, which is really interesting, especially the extrapolation that you mentioned, because I mean, your architecture is like a neural operator, right? So so this is a sort of and you now for the Gaussian process that you use for the U of t, a true out of distribution would be actually to go and test with a different correlation length. And I think in that case, you will not be able to, especially if the correlation length is smaller for the velocity. In that case, you will not be able to predict the dynamics because the dynamics has changed. But you are stuck to that correlation length. So as long as you learn the dynamics for that correlation length associated with the GP for U of t, yes, you can learn it, I think. But going outside that correlation length is smaller, it's tough.
I think that I agree with you that for the time being, when people talk about extrapolation, is always time extrapolation within the parameter space that was already observed. But being able to go beyond the parameter space of physics-based parameters while getting at the same time extrapolation is something that we definitely have to work on. Unless you have a paper that I'm not aware of.
No, it's very difficult. If the correlation length is larger, we have shown that it's okay. If the correlation length is smaller, you have to train further, and it's difficult.
Okay, thank you for the comment. That was really useful, I think.
Yeah. Thank you very much for your talk.
Of course, it was my pleasure to be here today, and thanks for the kind invitation again.
Thank you. Do we have any other questions? Yeah. Vivek, do you have?
Yes, I have a question. Hi, my name is Vivek, and I'm a PhD student working with Professor Karniadakis. So it's regarding the same slide. So if I looked at the architecture of the model, I saw that you are feeding in as input U of t and predicting Y of t as the output.
Yes.
Of the latent. Yes. So for the case of the lid-driven cavity problem, can you please tell me what your U of t and Y of t is?
Yeah, so U of t is, so here you see that the velocity is fixed to 0, as no sleep boundary condition for these three borders. And then U of t, as Professor Karniadakis was saying, is sampled from a Gaussian process with a fixed correlation length and a certain amplitude. And the output is actually UX and UI. So it's a two-dimensional output. In the sketch, for the sake of illustration, I just put one output, but here we are actually getting the whole velocity field in 2D.
Okay, I understood. Thank you.
Yeah.
Also, regarding the temporal extrapolation part, so
yes,
what is the temporal domain you use for training, and what is the temporal domain you use for testing?
So we use 0.20 for training, and then twice as much for testing. We really make sure that we are going further beyond with that.
All right. Thank you. Great talk.
Of course.
Thank
you very much.
Thank you. Do we have any other questions? I cannot see. That's it. So it's time to close the session. Thank you, Alexander and Matthew, for accepting our invitation and for your time for the talk. Thank you, everybody, for joining us today. So I hope everybody have a great weekend ahead. Bye.
Thank you very much. Bye-bye.
Bye.